Chapter 5. Fields, Laplace's equation in 3D in Chapters 4 through 7. Classic electromagnetism (EM) is covered, with extensive coverage on the Lorentz transform. EM is Lorentz invariant in Chapter 8, which then leads to special relativity and general relativity and other topics in later chapters. This chapter, Chapter 5, is entirely focused on solving a class of ordinary differential equations, ODEs, known as the 3D Laplacian, that describes many of the electrostatic systems indicated in the preceding chapter. This will bring forth some of the main techniques for solving ODEs in general. Thus, the chapter is complemented by the material on advanced ODEs in Appendix D and introductory ODEs in Book 1-1 Appendix A. We will see the role of choice of coordinates and of symmetries. We will see the fully detailed solution of the classic Legendre and associated Legendre ODEs, and we will see Green's function methods.
For Chapter 5 there is, once again, use of notes and conventions from Jackson 32, however, there is also further details on ODEs from 43, especially in Appendix D, and from related coursework in Applied Mathematics at Caltech, see Problems and Solutions in Appendix D. The physically motivated methods for solutions, method of mirrors, asymptotics, reveals that many of the methods to solve ODEs were developed by physicists. As mentioned previously, especially in Book 1-1, a physics solution often reduces to solving an ODE, and the set of such ODEs relevant to physics is limited, and most will be covered in this series. Being able to solve the Laplacian class of ODEs is critical, and of these we only really need the 3D case. This is because we are generally working with 3 spatial dimensions, no more, and if symmetry allows us to reduce from 3D to 2D, then Sector 2.2, Appendix A show that use of the Schwarz-Christoffel transform allows the most complex boundary conditions to be transformed into something trivial. So we need only focus on Laplacians in 3D to complete our understanding of this branch of ODEs relevant to physics.
Note on examples and exercises the chapters on electromagnetism draw, foremost, from the excellent source, Classical Electrodynamics by J.D. Jackson 32. That was the required text for many years at Caltech. Many of the Jackson problems develop the physics theory further, e.g., Gauss's theorem, or further develop the mathematical techniques, for ODEs, definition of delta function as limit, etc. With my own notes from the courses at Caltech, and upon later preliminary exam review at the Universal Wisconsin, the addition of the completed problems from various sources were acquired in a way that seemed to provide a mapping of understanding. I wanted to convey that understanding here. Solutions to these key problems are carefully worked out in what follows, along with notes on the theory from Jackson as well as from 33 to 35. Basic exercises are given to rederive or verify the theory. The solutions to the exercises here, for the most part, are available via the aforementioned Jackson text, with the detailed derivations provided there.
Many examples and related problems are done in order to cover material from basic undergraduate problems to advanced engineering, for antenna design, say, so the notes and problems also draw from undergraduate and graduate EM class notes/exams, and the other texts mentioned, 33 to 35. The remarkable success and modern applications of EM will be made evident, but at the end of Chapter 7, when we carefully analyze the hydrogen atom, we will find that there is radiative collapse in the classical theory. This fundamental flaw in the theory, when dealing with even the simplest bound atomic system, will be corrected with the development of the quantum theory in Book 4-15.
5.1 Spherical coordinates, notes/conventions from Jackson 32 Chapter 3. Let's now consider Laplace's equation in spherical coordinates. See equation 5-2 that follows. Thus, see equation 5-3. Since see equation 5-4 that follows, we have see equation 5-5. Use phi equals u of r over r p of theta q of phi with gradient squared phi equals 0.
See equation 5-6 that follows. 3 separable equations result. See equation 5-7. In order that q be single-valued, m must be an integer, if the full azimuthal range is allowed. See equation 5-8 that follows. And see equation 5-9. If we substitute x equals cosine theta, this becomes the generalized Legendre-equation.
See equation 5-10 that follows, whose solutions called associated Legendre functions. The ordinary Legendre equation is obtained when m squared equals 0. See equation 5-11. For the solution to the latter, a power series is used. P of x equals x to the alpha th power, the sum from j equals 0 to infinity of a sub jx to the jth power, which upon substitution becomes, see equation 5-12 that follows. Since the coefficient of each power of x must vanish separately, for j equals 0, 1 we find, see the following equations. And for general j,
see equation 5-13. It is sufficient to choose either a sub-0 or a sub-1 different from 0, but not both. Let a sub-0 is not equal to 0, then alpha equals 0 or alpha equals 1. Alpha equals 0, right double arrow even power series, and alpha equals 1, right double arrow odd power series. Properties of series. Want a finite solution at x equals plus or minus 1, so series must terminate. The recurrence relation will terminate only if script L is 0 or a positive integer. And even then only the even or odd power series will terminate, alpha equals 0 times OR times alpha equals 1. Let's examine properties of Legendre polynomials, including, starting with the ordinary Legendre equation, m squared equals 0. See equation 5-14 that follows. The solutions are Legendre polynomials, whose compact representation can be given via Rodriguez formula. See equation 5-15. Substituting, we can show orthogonality. See the equation. Or see the equation shown.
Exchange indices and subtract. See equation 5-16 that follows. For script L, script is not equal to script L prime right double arrow ORTH of OG of ONAL. For script L, script equals script L prime. See equation 5-17. Using see the equation, we get,
see equation 5-18 that follows. So, 2 script L script plus 1 times and subscript L equals 2 script L script minus 1 times and subscript L script minus 1, thus 2 script L script plus 1 times and subscript L is independent of script L. Solving for script L, script equals 0 right double arrow P sub 0 of x equals 1 right double arrow n sub 0 equals 2 right double arrow 2 script L script plus 1 times n subscript L equals 2, we get n subscript L equals 2 divided by 2 script L script plus 1, thus see equation 5-19. To make orthonormal, e.g., the integral from a to b of u sub n raised to the asterisk power of epsilon u sub m of epsilon d epsilon equals delta sub nm, define as, see equation 5-20 that follows. For the Legendre series, rep of any function f of x on the interval -1 is less than or equal to x is less than or equal to 1, see equation 5-21.
The recurrence relations follow from the original Legendre equation and that generated by Rodriguez formula. See equation 5-22 that follows. So, see equation 5-23. For potential problems in conical holes or near a sharp point lightning rods, Legendre functions of the first kind in order V, R, N, Hall, J, APPL, Phys. 20, 925, 1949, 117. Additional theorem for spherical harmonics. See equation 5-24 that follows. Laplace equation in cylindrical coordinates gives rise to the classic Bessel functions.
See equation 5-26.